Thanks so much for the introduction. Hello, everyone. Exactpro focused on mission-critical technology and software testing for mission-critical technology. We work with exchanges on all continents in more than 20 countries. Exactpro works with half of top 20 global exchange groups. We have quite a lot of information published on the subject. We were part of large exchange group. Now we are independent software testing business and continue to provide functional and non-functional testing across the globe. The business has many awards in this area. And personally, I'm available to be connected on LinkedIn. Apart from working in Exactpro, I also represent several very nice organizations that I would like to recommend. First of all, I represent Exactpro in Zero Outage Industry Standard. It is an organization focused on improving resilience of complex technology platforms. I'm also co-chair of fixed trading community work group, MOST, monitoring, onboarding, and software testing. It's very likely that your firm is a member of fixed trading community, so please do have a look. And also, I'm working with university. I'm head of LOST, laboratory of software testing. If you have any research-related interests, please feel free to contact me on the subject. So after many years of working in software testing, when I need to learn something about it, I Google it, and software testing, the definition of software testing, the top articles on the subject claim it to be art, science, research, craft, engineering. So there is a continuum from art to engineering. Most tools vendors will claim it to be engineering, and others will say that it is more craft. I would like to start with looking at the differences between engineering and science. There's a very nice book on nanotechnology called Radical Abundance, and there is a very clear description of the difference between science and engineering. So engineering turns a model into a useful product, and science looks at the physical reality, at the systems, and turns it into a model. So the difference between science and engineering is an anti-parallel flow of information. So to correctly place software testing, we need to have a look at what software testing is. Software testing is exploring software with intent of finding bugs. So the main thing about software testing is finding defects. And software testing is empirical technical investigation conducted to provide information service to the relevant stakeholders. So software testing, the main measure of good software testing is its ability to identify defects, and also it conveys information. So if we will try to compare software testing with development, we also see the clear anti-parallel flow of information. In development, we are trying to convert an abstract idea into a useful product, system, service. In software testing, we are trying to get information about object of study, about software, and improve our understanding of this software. So these are two completely different processes. And understanding your software has many advantages. At the moment, quite a lot of assets in most of the modern companies are in technology. So whether you understand the technology or not is important because it can help you to improve your technology investment decisions. So software testing is different from software development in the same way as science differs from engineering. And one thing that we can notice on this diagram is that the key foundation of both processes are models. All testing is model-based testing. So in every single case, there is some model. Quite often, these models are implicit and exist only in software testers' head. But there are also cases when these models are more explicit, more formal, and can be used to drive software testing. Model as a concept has several important features. The first one is mapping, so it reflects some part of reality. The second one is reduction, that it stands for some simplification. So it is not possible to create a model that will reflect all aspects of any real object. So reduction feature is always present. It always contains a simplification of reality. And the last very important thing is pragmatic feature of the models. So in software testing, the only true purpose of software testing is to find defects and provide information. So pragmatic property of software testing models is whether they help to reveal defects or whether they help to conceal them. Good models help to reveal bugs, bad models help to hide them. So what we'll try to apply model-based testing concept to two main approaches that we frequently encounter across our client base, across our industry. And the first one is behavior-driven development. The first thing with behavior-driven development is that there is a very clear flow of information there. We have a model represented in simple sentences with domain language that can be linked through regular expressions to the actual code, to step definitions, and teams work collaboratively to turn this model into useful product. It is very clear that BDD is engineering process, it is software development process. It has nothing to do with software testing. My colleagues already tried to explain it at different key financial events in New York and Milan, but main thing is that most of complexity is hidden in steps definition, and it is not immediately clear what is broken, what is better when people look at the feature files. We've encountered quite a lot of people who are willing to explore and review BDD scenarios, but proportion of people who are willing to have a look at the step definition source code is much smaller. So BDD is also a model model-based testing, but it is more applicable to engineering rather than to testing. Another very common approach to increase software testing efficiency that we encounter in clearing post-trade systems and in trading as well is parallel run or side-by-side comparison with the previous versions of the system. So to a degree, a regression testing. In this case, there is a model. So it is also a model-based testing, but as a model, one uses the previous version of the software, and the main assumption is that the new version should work in the same way as the previous one. So this approach have both benefits but many limitations related to changes in data formats, in new functionality. So on top of similarities, we need to implement additional models that will describe differences between new software and the old software. And in real life, we frequently encounter that people try to fight these discrepancies by introducing many additional steps to get rid of all discrepancies. It sometimes leads to hiding problems, hiding defects, rather than bringing them to the human's attention. As any other process, it is possible to improve efficiency in software testing by using tools. And the key thing here is that any efficient testing is a testing capable of finding bugs. So if we have a test process capable of finding defects, we can improve its efficiency. If we are not looking at the process capable of finding defects, we are likely only to magnify its inefficiency. Software testers there frequently use term manual software testing. Manual labor is using muscles, and in reality, if we as software testers were using muscles, that often an average software tester would be more fit compared to the current situation. So most of the time we rely on other parts, and tools are objects that enable us to extend our abilities, so to extend our abilities as hands, eyes, and brains. So when somebody is thinking about replacing part of the human, one needs to think about all three. So it is necessary to replace hands, to replicate human eyes, and also to get rid of human brains. Mechanization is adding additional power source to repeat something, and automation is technology by which a process or procedure is performed with minimal human assistance. So whether it is possible to remove human assistance from research, from science, from getting information, it is a difficult question, and once again there are debates on the subject. In particular, model-based testing is a complex and nuanced field with lots of research. The latest state-of-the-art review contains references to thousands of peer-reviewed papers. One of the most cited one contains taxonomy of model-based testing approaches. And the good thing about it is that it is possible to split various parts of testing, such as test generation, test execution, and model specification. This allows to clearly see what parts can be easily mechanized or automated, and what parts require quite substantial human involvement. So among all software testing is model-based testing, but a more narrow definition of model-based testing would be the testing that is based on more formal models. For example, when specifications or models are expressed in some machine-readable, well-defined notations. In fixed trading community, several last years were spent on developing fixed orchestra machine-readable specification for fix and other interfaces when you work with different APIs to try to use more narrow model-based testing. You need to think whether it is possible to present these specifications in machine-readable formats. Then, in a narrow sense, model-based testing also uses more formal test generation and test selection, because when you can use algorithm to generate lots of tests from a good model, it is likely that no computational capacity will be enough to execute all of them. So it is necessary to also apply one or another test selection approach. And of course, it is necessary to have a way of automatic checks, test oracles, in order to decrease load on the humans, so they can review not the whole set of information, but somehow decreased one. So it is very important to, when we look at automation, to distinct what can be achieved through automation. So we can, at the current level of technology, build a car that can go from one point to another, but we still rely on humans to specify start and end points, and also to work on the models that underlie autonomous vehicles. It is very important to constantly improve these models, and it is not an easy task. So humans have quite a lot of fun, especially recently, dealing with complex models, especially with models that we have to rely on to make important decisions related to both our well-being and prosperity of our societies. And of course, you've all heard about these models, correct and incorrect outputs, and correct and incorrect decisions. In software testing, good, massive, automated library represents a very complex model. So humans have to deal with this complexity, and key things about it is that all models are wrong. So, and all models are approximations. However, some models are useful, and it is necessary to make decisions based on wrong, simplified models, trying to cut our problems down to size that a human can comprehend the output of these models. Of course, there is always a danger that when we are using simplified models, we are limiting ourselves to a small subset of the object without understanding the full picture. Looking at how humans understand the output of complex models in software testing, we can see two main extremes. The first one is when somebody is looking at a large ensemble of complex models that give something, some results. The first step is to say that it is not possible to review all this complexity, and in order to proceed, we need to have a simpler model. Very often we see that for huge platforms like clearing platforms, and small simplified libraries are created, like 200, 300 test cases that can be easily reviewed and understood by people. It is not a problem to use a simplified model, but when it is used instead of a more sophisticated solutions, it leads to the issues that you can build a plane from straw and sticks, stones, but it is unlikely to have the same level of reliability as the real thing. Another opposite extreme is when people take the output of complex models for granted, so follow the science. We have models and they give us precise answer. We just need to convert it into red, yellow, green charts and base all our decisions on them. It is the opposite extreme, and of course it also leads to problems when the models are not scrutinized, not studied, and not really understood. So if you trust something blindly, you do not really understand it. In Exactpro, we acknowledge that all models are wrong. So we are trying to use a common concept used in cybersecurity and systems reliability, defense in depth, when we use lots of diverse models to describe the systems under test and to generate scenarios. We expect that most of the models will miss most of defects, but the idea that there will be at least one or several capable of identifying problems. In order to support this approach, we are working on developing open source microservices-based, Kubernetes-based platform, TH2. And the key idea behind it is that we can run many different models in parallel. So we can both generate test scenarios, execute them, and process. And there is not a single thread for processing the data, but the system allows us to generate lots of tests, but also to apply different models to analyze whether we see necessity to notify a human or not. There are multiple challenges with applying MBT. Research literature in particular highlights three of them. The first is related to process, the second is related to platforms, and the third is related to people. On the first one, what we can see, so if it is necessary to develop complex models before testing can start, it sounds absurd, but very frequently we receive requests to have all test scenarios, so essentially to have the full model of the system before the testing will start. It is possible to do things like that if you have an extreme amount of money to fund it. In any other case, complex models should be developed in parallel with the actual software development. So sound engineering is based on science, and science uses instruments provided by engineers. These two processes, they have anti-parallel flow of information, but they should work simultaneously to achieve better results. So the model should not be created in advance. Of course, for complex systems under test, it is necessary to abstract quite a lot, and by understanding it, the idea is to create lots of models, intersecting models, to cover something instead of creating a complete replica of the system. In some domains, it makes sense to have several independently created replicas of the system to serve as a model to generate test scenarios and test oracles. There is also important perception that using model-based testing and understanding formal models, writing code that will be able to generate scenarios from these models requires a higher engineering skills, but we think even more important is to have what is called scout mindset, the motivation to see things as they are and not as you wish them to be. Good software testers, they deal with the reality, and they need to understand that they are providing information service rather than building a product. When you start building a product instead, you focus on what you wish to have and not what you have at the moment. In Exactpro, we provide managed software testing service built on three important pillars, such as processes, platforms, and people. Our main process is that we think that software testing is finding defects, and software testing is information service. This drives all our work. Platforms allows us to build diversity of models and use them to generate lots of scenarios. And the main thing is, of course, people capable of understanding these processes and platforms. If you have any questions about what we do, please feel free to talk to us. Thank you. Thank you very much.